Here comes the party!
Hello, good morning, sir. Good morning, everyone. And my name is Alorins Bisameni, together with Christian Lirimole, and we are the reporters of Belts and Pulleys. Definition. So, pulleys can be seen in more than one form as they serve a variety of purposes in the industrial world. First, a pulley is a wheel on an axle or shaft designed to support movement and change direction of a belt or taut cable. The device helps in power transmission using a cable or belt. In a belt and pulley system, a belt runs along a pulley's groove so that the power can be transferred either from one pulley to another or from the pulley directly to the application that requires power. So as you can see here in the diagram, this circle is the pulleys and attached to it is the belt. Pulley is also used to guide a cable or exert a force, and it changes the direction of force, making pulling down easier than lifting up. These kinds of pulley may be called sheave. A sheave or pulley wheel is a grooved wheel often used for holding a belt, wire, or rope and incorporated into a pulley. Functions. The primary function of a belt is to transfer power from one source to another, whereas pulley that has a groove around its circumference allows a belt to smoothly through it when transmitting rotational motion. Second, it is designed to attain different diameter functions as it is used to increase or decrease the speed of the application of its power. Third, a specific type of pulley is used to change the direction of the force. This pulley is often seen on heavier applications and they are not used for transmission of rotational motion. The function of a belt is to exert force from one direction to either vertical or horizontal direction. Pulleys that are not used to transmit rotational motion functions as they are used to lift heavy loads. The pulley helps reduces the amount of force required to lift a load. Finally, the function of a belt is to exert force from one direction to either a vertical or horizontal direction depending on the position of the energy source and position of application it will be powering. Applications of belt and pulley. In applications where belt drives on a pulley, they are used in automotive engines such as cars, trucks, buses, stationary power generators, marine engines, aviation engines, and etc. Belt and pulley are also used in air compressor engines, agricultural equipment, conveyors, and etc. In fact, a belt and pulley are purposely designed on any application that requires a rotational motion from another source. There are tons of machines and equipment out there, from larger ones to smaller ones, such as winches, treadmills, and washing machines. Belt drives. Below are example of the application of a belt and pulley. First is in a bulldozer, it is used to do its lifting, an extended ladder, using a crane in a construction site, the working of an escalator going up or down, opening and closing a garage door, belts and pulley in vehicle, elevation uses a several pulley in its working. So belt drives. Belt drives are a type of frictional drives used for transmitting powers. It is a pair of pulleys attached to usually parallel shafts and connected by an encircling flexible belt that can serve to transmit and modify rotary motion from one shaft to the other. So nara ang iyahang pulley o ang belt. So mechanical power or rotational or rotary motion is transmitted from one driving pulley to the driven pulley. So the smaller pulley is called the driving pulley while the bigger pulley is the driven pulley. The portion of the belt which is having less tension is called a slack side. The one which has higher tension is called tight side. Here in the photo. The tensions in the tight and slack side of the belt depends on the angle of contact. The belt drive have to be arranged such that the slack side comes above and tight side comes below the pulley. Angle of contact. Types of belt: flat belt, V belt, and circular belt. Flat belt. This belt has a rectangular cross section, and these belts are capable of transmitting power over long distances between pulley centers. The efficiency of this drive is around 98% and produce a little noise. Second, V belt. V belts are also used with groove pulleys. V belts are trapezoidal in cross section. These belts permits large speed rotation and can transmit higher power. Circular belt. The circular belt has a circular cross section and is used with the groove pulleys. It is mostly used in the factories and workshops, where a great amount of power is to be transmitted from one pulley to another when the two pulleys are more than 9 meters apart. Types of belt drives. First, open belt drive. Second, cross belt drive. Third, step cone pulley or speed cone drive. Fourth, fast and loose pulleys. Fifth, jockey pulley drive. First, open belt drive. In open belt drive, the belt is employing when the two parallel shafts have to rotate in the same direction. This is because when the upper side becomes the slack side, it will sag due to its own weight and thus increase the arc of contact. Second, cross belt drive. In cross belt drive, the belt is employing when two parallel shafts have to rotate in the opposite direction. At the junction where the belts cross, it rubs against itself and wears off. To avoid excessive wear, the shaft must be placed at a maximum distance from each other and operated at very low speed. Third, step cone pulleys. In step cone pulleys, belt drives are used when the speed of the driven shaft is to be changed very frequently, as in the case of machine tools such as lathe, drilling machine, and etc. A step cone pulley is an integral casting having three or number of pulleys of different sizes, one adjacent to the other. One set of step cone pulley is mounted in reverse on the driven shaft. An endless belt will be wrapped around one pair of pulleys. Fourth, fast and loose pulleys. In fast or loose pulley, belt drives are used when the driven or machine shaft is to be started or stopped whenever desired without interfering with the driving shaft. A pulley which is keyed to the machine shaft is called a fast pulley and run at the same speed as that of the machine shaft. A loose pulley runs freely over the machine shaft and is incapable of transmitting any power. And lastly, the jockey pulley drive. In an open belt drive arrangement, if the center distance is small, or if the driven pulleys are very small, then the arc of contact of the belt with the driven pulley will be very small, which reduces the tension in the belt. Or if the required tension of the belt cannot be obtained by other means, an idler pulley called jockey pulley is placed on the slack side of the belt. This increases the arc of contact and thus the tension which results in increased power transmission. Belt drive advantages and disadvantages. Advantages: it is flexible, simple in construction, smooth operations, efficient at high speeds, and protect against overload. Running and maintenance cost is low, and also relatively long life and easy to work with. Moving on to disadvantages. Loss of power due to slip and creep in turn results in low efficiency. It is not preferred for short center distances, and the endlessness of the belt joint reduces the life of the belt. Also, you have to retention it periodically. Deterioration from exposure to lubricants or chemical, and it cannot be repaired. It must be replaced.
So now we will solve some of the sample problems of belts and pulleys. So first we will find out how to get the length of the belt. So in this figure here we have a center distance of 600 millimeters and a largest pulley, which is the pulley number 1, with a diameter of 200 millimeters, and the smallest pulley, which has a diameter of 100 millimeters, and the length of the belt there is a known. So for us to get the length of the belt, we need to use this equation: pi times PD1 plus PD2 times 0.5 plus 2 times the center distance plus PD2 minus PD1 squared over 4 times the center distance. So substituting all the values will give us this: 3.142 times 200 millimeters plus 100 millimeters times 0.5 and so on. So we need to simplify this, and we will get 3.142 times 300, the sum of this one, times 0.5 plus 1200 millimeters plus the simplified form of this, which is equal to negative 100 millimeters squared over 2400 millimeters. So we still need to simplify, then we will get 471 millimeters plus 1200 millimeters plus 4.167 millimeters. So now we don't need to simplify, and then by adding this 3, we will get to have the length of the belt. So the length of the belt must be equal to 1675 millimeters. So what if we don't have the center distance, but we have the length of the belt? So to do that, we have the equation 4 times the belt length times 6.28 times PD1 plus PD2 plus the square root of 4 times the belt length minus 6.28 times PD1 plus PD2 squared minus 32 times PD1 minus PD2 squared over 16. So substitute all the values, then we will get 4 times 1675 millimeters minus 6.28 times 200 millimeters plus 100 millimeters and so on. To simplify this, then we will get 4 times 1675 millimeters minus 6.28 times the product of this one, I mean the sum of this one, which is equal to 300 millimeters, plus the square root of 4 times 1675 millimeters minus 6.28 times the sum of this, which is also equal to 300 millimeters squared minus 2 times 100 millimeters squared, which is the difference of this, over 16. So simplify this furthermore, then we will get 6,700 millimeters minus 1,884 millimeters plus the square root of 6,700 millimeters minus 1,884 millimeters squared minus 32 times the 100 millimeters squared, which is equal to 10,000 millimeters over 16. So we still need to simplify. Then we will 4,816 millimeters, which is the difference of this one, plus the square root of 4,816 millimeters squared minus 320 over 60. So simplify 4,816 millimeters plus 4,816 m squared millimeters squared, which is equal to 23,193,856 millimeters minus 320,000 millimeters over 16. So we still need to simplify, and we will get 4,816 millimeters plus the difference of this one will be equal to 22,873,856 millimeters over 16. So our center distance must be equal to 600 millimeters. So that's our center distance. So that's how we get the length of the belt and the center distance of this example. So in this example, we going to find the tension that deals with belt frictions. So we have two coefficient static frictions here that will help us to solve the tensions later. So what we have here is we have a rope that is wrapped around twice in the pole, which has a tension number 2, which is equal to 1000 newtons. So the question is, how much force is required in T sub 1 or in this tension to hold the rope from slipping so that the rope stays stationary? So we have a formula here that will help us solve this problem. So we have the formula of T sub 2 over T sub 1 equals E raised to mu sub s times the angle of contacts. So these are our angle of contacts in this equation, in this problem. So rearrange this equation for us to get the T sub 1. So by rearranging this formula, we will get to have T sub 1 equals to T sub 2 over E raised to mu sub s times the angle of contacts. So we need to calculate first this coefficient static friction, which is equal to 0.2. So substitute all the values in this equation, in this formula, then we will get T sub 1 is equal to 1000 N over the coefficient static friction, which is equal to 0.2 times the two revolutions here. So since one revolution is equal to 2 pi, then we will have 4 pi here. So calculating this one will give us our T sub 1, which is equal to 81 newtons. So next we're going to find its tension with this coefficient static friction. So substitute all the values will give us T sub 1 is equal to 1000 newtons over 0.4 times the two revolutions, which is equal to 4 pi, and calculating this will give us T sub 1 is equal to 6.56 newtons. So as you notice guys, the tension that is required to hold the rope from slipping here is getting smaller as the is the coefficient static friction increases. So that's how we will get the tension, this type of problem. So in this example, we're going to find the velocity ratio and the output speed of a pulley. Example, a driven pulley has a diameter of 120 millimeters and a driver pulley has a diameter of 40 millimeters. So to find the velocity ratio, we need to divide the diameter of the driven pulley by the diameter of the driver pulley. So 120 millimeters over 40 is equal to 3. So now we have our velocity ratio. We can now solve the output speed. So the output speed is equal to input speed divided by the velocity ratio. So we have an input speed of 100 revolutions per minute and our velocity ratio is 3. So 100 over 3 will result into 33 revolutions per minute. So in this example, we're going to find the acceleration and the tension of a pulley. So a string is placed over a massless and frictionless pulley. A mass of 8 kg is suspended at one end, while a mass of 5 kg is suspended from the other end. What is the acceleration of the system? So in this video guys, we have two tensions on the string, we have two masses, and two forces of the object pulling down. So since M1 is heavier than M2, then we can assume that the acceleration will fall in this direction. So remember that the forces that opposes the acceleration will be considered as the negative force. So for us to calculate the acceleration, we need to use the Newton's second law, which indicates F is equal to ma. So rearrange the formula, we will get to have the acceleration. So acceleration is equal to force equals mass. Force over mass. So since we have two masses and two forces acting on the system, then our formula will become like this. So A is equal to the F net over the total mass. So substituting all the forces and the masses will give us m1g, and since m2g is opposing the acceleration, it is considered as negative, so we will have minus m2g here over the total mass, which is equal to m1 plus m2. So factor out the numerator, then we will have m1 minus m2 times the gravity over m1 plus m2. So substitute all the values altogether. So we'll have 8 kg minus 5 kg times the gravity, which is equal to 9.81 meters per second squared over 8 kilograms plus 5 kilograms. So this will give us 3 kilograms times 9.81 over s squared over 13 kilograms. So calculating this will give us our acceleration, which is equal to 2.26 meters over second squared. So now we will calculate the tension in the string with the use of this equation, T sub n equals mng plus mna. So the direction of the acceleration will determine whether the acceleration is positive or negative. So T sub 1 is equal to m1g, and since m1, the mass m1 is accelerating downwards, then it will become minus m1a. Substitute all the values, we will get to have 8 kilograms times 9.8 meters over second squared minus 8 kilograms times the acceleration, 2 meters over s squared. So calculating this will give us our tension in this string, that is equal to 60.32 newtons. So now we're going to find the tension number 2. So tension number 2 is equal to m2g, and since m2 is accelerating upwards, then it should be plus m2a. So substitute all the values, we will have 5 kilograms times 9.81 meters over second squared minus 5 kilograms times the acceleration, 2 meters over second squared. So that will give us the tension that is equal to 60.32 N. So that's how you get the tension in this problem. So in this example, we're going to find the acceleration and the tension of an incline. So this is an incline, guys. So first, we're going to draw its forces. So we have the force here that is pulling the object downwards, which is equal to m1g. and we have to divide this force into its components. So one of its components should be this one that is perpendicular to the incline, which is m1g cosine theta. And we also have its component here, which is parallel to the incline, which is m1g sine of theta. Then we have the normal force, which is equal to m1g cosine theta. So since we have divided this into its two components, then we have to cancel this out. And since the normal force and the force that is perpendicular to the incline is equal, so we also have to cancel this out. So we also have a force here that is pulling the object downwards, then that must be, and that should be m2g. So now that we have left with two forces, and then it should look like this. So since 10 kg is heavier than 8 kg, so our assumed direction of acceleration will fall in this direction. So to get the acceleration, we have a formula of F net and the total mass. So acceleration is equal to m2g minus, and since m1g sin theta is opposing the acceleration, so it will become minus m1g sin theta over m1 plus m2. So substitute all the values, then we will get 10 kilograms times 9.81 meters over second squared minus 8 kilograms times 9.81 meters over second squared times sine 30 degrees over 8 kilograms over 8 kilograms plus 10 kilograms. Then we will have 98 newtons minus 39.2 newtons over 18 kilograms. And by calculating this, we will get to have our acceleration that is equal to 3.27 meters over second squared. So now we will find its tension. So to find the tension, we will use a different technique, which is called the free body diagrams. So what you're going to have to do is you have to take the mass and draw its forces. So take the mass. So we have taken the M2, which has a mass of 10 kilograms, and the force here that is pushing the mass downwards, and we have the tension here that is pulling the mass upward. So we still need to use the Newton's second law, which is the F equals ma. Then substitute its forces and the acceleration. Then we will have m2g, and since t sub 2 is opposing the acceleration, so it will be considered as our negative force. So it will become minus t sub 2 equals the m2a, which is its acceleration. So to find the tension, we have to rearrange this equation here to get t sub 2 equals m2g minus m2a. So substitute all the values. 10 kilograms times 9.81 meters over second squared minus 10 kilograms times the acceleration 3.27 meters over second squared. So our tension should be equal to 65.3 newtons. So that's how you get the tension using the free body diagram.
Nice.